what I'm showing here is a block diagram of the SmartFusion2 devices. We have different members in the family, and there's a few options that may not be in all of the members. But basically, in this picture, we have two different colors. We have the blue color, and anything that's implemented in blue is implemented as a standard cell. So it's not programmable. So that would be the microcontroller subsystem, where we have the Cortex M3. We have an instruction cache. We have blocks of flash memory that we refer to as embedded flash memory, or ENVM. We also have blocks of SRAM, embedded SRAM, ESRAM here. And then we have some DMA controllers. We have what we call a peripheral DMA controller. We have what we call the high performance DMA controller. We have a number of peripherals. We have timers, UARTs, SPIs. We have a CAN controller. We have watchdog timers, typical in a system where you have a microcontroller or a microprocessor. We have something called the RTC, that's the real-time counter. You can use it for, you can use this as a timer, but you can also use it for timekeeping functions and calendar functions and things. We also have a hard DDR controller. When I say hard, I mean it's implemented as standard cell. And there's a DDR controller that supports DDR2, DDR1, and LPDDR memories. And some devices have a second one down here where you see this fabric DDR.
And the DDR is always off chip.
Right, so the DDR is off chip, but this is a controller that would be configured. You would specify the type of memory you're using, and then it would drive out the proper cycles. And there's even something called the DDR bridge that allows different people to make requests, and the DDR bridge will queue up requests and then burst them out to the memory in a way that uses the memory most efficiently.
So now the memory can both be accessed by the FPGA fabric in addition to the Cortex, correct?
Yeah, that's true. We have the FPGA fabric here, and we could put logic in the fabric that could access that memory if you wanted to. So we have these DDR controllers. Some devices have a second DDR controller called the fabric DDR controller. We also have high-speed serial interface blocks, these SerDes blocks that can implement different protocols like PCI Express or ZOE, XGXS, or you could just use it for native SerDes, and you just have your own serial protocol that you're using. We can run up to 5 gigabits per second. We can do PCI Express Gen 2 at 5 gigabits per second.
So on the demo boards where the PCIe connectors are, is that going through SerDes?
Yeah.
Okay.
Yeah, we've configured one of the SerDes blocks to do that. And then there's another block here called the system controller. That's another hard block, and that's a block that has a number of functions that are built in that have to do with putting the device in low power, like the flash freeze mode. We can use this to do programming. We can actually reprogram, say, the flash memory or the FPGA fabric. And we also have some other blocks that are used for authenticating the bit stream. This AES 256, so we encrypt the bit stream, and we always authenticate that before we do anything. If we try to reprogram, we have a secure hash engine that we can make digests of the fabric and the flash memory blocks, so that's how we can tell that they haven't been tampered with and that they're correct and it's the right configuration. And then on some of the devices, you can use some of these features to encrypt data that goes through the device. So we have something called an SRAM puff in some of the devices. They can be used to generate a seed for the random number generator, to generate keys and things. So we have some devices that have more security features than others.
Now the SRAM puff you were mentioning earlier is an interesting piece of IP. Could you elaborate a little bit on how that works on the physical level and what the capabilities of that are and applications?
Well, the SRAM puff is a private RAM block. It's about 2K bits. And it's used with some IP that we get from a company called Intrinsic ID. They've discovered a way that you can power up a RAM. If you have a random access memory and you turn off the power, it's a volatile device. So when you turn it on, there's going to be about a 50-50 chance that bits are going to come up high and bits are going to come up low. But they've done a lot of work, and they've determined that with a block on a particular device, that they can turn it on and they can reliably read out a certain number of bits that always come up consistently, either zeros or ones, out of this block of bits. And using their IP, we can read out these bits, and then we can use that to seed the random number generator. Now, whether or not a bit's going to come up 0 or 1 is going to depend a lot on semiconductor physics, oxide thicknesses, and things. So no two devices are going to be the same. So that's the kind of the interesting thing is it's almost like the device has its own fingerprint. You turn on this RAM block and you read out the bits and we extract certain bits, but we're not going to get the same bit pattern out of two different devices. And we can use their IP, we can read out these bits, we can seed the random number generator to use that to generate keys and things. And as a security precaution, that RAM block is only used when we're doing these cryptographic operations. So it has its own power supply, and normally it's turned off. Then we would turn it on, read out the bits, and then once we've done what we want to do, we turn it back off again. So there's a very small window where anybody could try to do an attack, try to figure out what keys you're using that you might be using to encrypt data or things like that. So it's a very interesting function, and it's available in the 060, 090, and 150 devices.
Now, you also mentioned some of the features of the Microsemi SmartFusion2 is the security features, in addition that you touched on mentioning about the AES and the encryption engines in it, but also some features as far as lockout and protection, reverse engineering protection. Could you weigh in a little bit on those while we're touching on this topic?
Sure. So we have some devices that we refer to as devices with data security features. They have an S suffix. And the devices have the S suffix allow you to use things like the AES and the SHA to encrypt your data. The larger devices have this SRAM puff. But there's other places that we have security measures for those devices as well. We have something called the AHB bus matrix. And the AHB bus matrix is not quite a fully populated cross-point switch. But what it does is it allows up to 7 masters to access the peripherals. So one of the masters is the Cortex. We have DMAs that are masters. We can have masters in the fabric. We have an interface here called the Fabric Interface Controller. There's one Fabric Interface Controller on all the devices. A couple of the devices in the family have 2 of them. So you could put a master out here in the fabric, and that master could access the memories, the flash memory, the ESRAM, the peripherals, and so on. Well, we have the ability in the security devices that we can block off certain masters from being able to get to certain memories. So if we have some data that we don't want every master to be able to access, we can block that off in the S devices. Other things we can do, we can have partitions in the flash memory that we can block off from certain masters. And so we have the ability to prohibit some masters from getting at certain memory slaves if we want to. And that's something that a user would do. And then we have other anti-tamper detection mechanisms in the device. So we can tell if somebody's trying to access the device through the JTAG. We can tell if they're trying to access the device in other areas who we call a security mesh. And if somebody is doing something that we detect as tampering, we can decide what we want to do about that. We could do nothing, but we could erase the device where it could be reused, or we could make the device in a state where it's permanently disabled. So depending on the application, who the customer is, what they're doing, what they've made, they may want to decide if they detect any tampering, they'll just make the device completely inoperable.
So now some cases where national security or device security or regulation are in there, this destruct mechanism in essence would be extremely important. Can you weigh in on some of those applications that?
Well, it could be, let's say we are in a secure military radio or something like that. Somebody is, somehow, that falls into the hands of somebody that we would prefer not have that. They start tampering, maybe try to reverse engineer it. We can detect the tampering, and then we can put that device in a state where it can never be used again. So it's inoperable, and then they can't gather any kind of information about the device or about that design.
Great.
So this is SmartFusion2. What I haven't mentioned yet is the FPGA fabric. So we have this FPGA fabric here, and the FPGA fabric consists of a logic element that's a 4-input lookup table with a D flip-flop, and then we have 2 different size blocks of memory. We have what's called the micro SRAM. That's a 1K block of memory. It has 1 write port and 2 read ports. And then we have what we call the large SRAM, which is an 18K bit block of memory. It can be configured to be a 2-port RAM, or I have a single read-write port, or it could be a dual-port RAM, where I have 2 read-write ports. And then we have what we call math blocks. The math blocks are hard multiply accumulate blocks where we have an 18 by 18 multiplier and a 44-bit add subtract that we can do with an accumulation function with. Those are typically tied for mathematical type of operations and DSP kind of operations like filters or FFTs or something like that.
Could you weigh in a little bit about how this could be applied to DSP?
Sure, we have some applications and some cores where you might use SmartFusion2 to do a filtering operation like a FIR filter. You might use it to do an FFT type of operation. And there's various ways you can design to do that, but we even provide some cores that people can use to do those types of DSP functions.
Now, one thing you mentioned are multiple cores that can be added into it, and you were mentioning about Core ABC. Could you weigh in a little bit on that?
Well, we provide in the software some cores that you can use when you're doing your design. And I mentioned that it's possible to have a master out here in the fabric that could access these peripherals and various different things. You could envision maybe a design where the Cortex is busy doing something and you might want some sort of an offload engine to do some other function. We provide a core that's a proprietary core called Core ABC that could do that for you. You could put the core out here in the fabric and you could communicate. We have a core called Core Mailbox you can use to communicate between the two, the Cortex and the Core ABC, and you could use that as an offload engine. So Core ABC might actually run things faster than the Cortex, and while it's off doing something, the Cortex could be doing some other operation, and then Core ABC could just put the results in the mailbox, and then the Cortex could just go back and read the results out of the mailbox. So we have the possibility of having a multi-master system with SmartFusion2 if we wanted to do that.
And then as far as Core ABC, I know there's some other cores that are available for prior third generation products, flash products. Can you, I'm sorry, FPGA products. Can you also mention just in other prior versions what other cores are available?
Well, in the third generation flash families, we have an 8051 core that could be used in any of those devices. And we also have a soft ARM Cortex M1 core and a soft ARM 7 core. And when I say soft, I mean it's implemented in the FPGA fabric instead of being implemented as standard cell like we have up here. Those cores are available in some, but not all of the third generation flash parts. They are not available for SmartFusion2 or Ignite.
Great. And one other thing that you were mentioning to me before that I was wanted a little bit more information on is programming the SmartFusion2 via JTAG versus SPI. Can you weigh in a little bit on that? Well,
we have various different methods that you can use to program the devices. And when we program the devices, what we're going to do is we're going to program the flash interconnect switch that allows us to configure the logic, configure the IOs. And there's some places in, even in the block up here, you see our purple where we can configure those. We can configure the watchdog timer for the timeout. We have a block called the sysreg block, which is a block of registers that configures the microcontroller subsystem. Those are typically written by the processor, but they can be programmed with flash switches. So normally when we're programming, we go through the JTAG interface, or at least one of the methods is to go through the JTAG interface, and we use the system controller and we can program. But we also have some other modes that we can use to program, maybe for doing updates in the field and things where we don't want to connect the programmer. And we can connect a SPI flash to the device. We have a dedicated SPI port that's part of the system controller that would allow me to put a flash memory out here that has an updated programming file, and then I could use the system controller to come in and I could either reprogram the flash memory or the FPGA fabric or both.
Now, one thing that is the benefit of the SmartFusion2 is having flash cells versus SRAM cells as far as the logic elements of the FPGA are concerned. Can you weigh in a little bit about that technology?
Yeah, it's a different technology than what you would see, say, in a Xilinx or Altera FPGA that are SRAM based. For starters, it's non-volatile. So an SRAM device is a volatile device. When you turn off the power, you lose the configuration, you have to reconfigure it. that can actually cause problems if you're in like a brownout condition where suddenly maybe you lose a configuration, you have to reconfigure when you're trying to be in normal operation. The flash switch that we use for our interconnects gets programmed at programming time, and we program a floating gate that stays programmed even when you turn the power off. So it's a non-volatile technology. You don't have to worry about brownout conditions and things causing the device to lose its configuration. And it has some other benefits as well. It tends to be lower power. It also tends to be more secure because you're not programming the device every time you turn the power on, which gives you a vulnerability where somebody could try to see your bit stream. There's ways that have been published to extract the keys that are used when the bit stream is encrypted. And if you have the key and you have the bit stream, then you can reverse engineer the design. You could even conceivably modify the design and then inject it into the part at programming time for some malicious intent. Well, I mentioned that we have this logic element that's a 4-input lookup table. It's kind of standard. You'll see that in Xilinx and Altera. Many of their families have the 4-input lookup table. It has a D flip-flop. You can bypass the D flip-flop and just use the logic, or you can connect the logic to the flip-flop. We have these memory blocks, and we have two sizes of memory blocks because sometimes you need a smaller block of memory, and just having one larger memory is kind of wasteful. So we have this small memory block, the micro SRAM. It's 1K bits. You can configure it, make it wider or deeper by using multiple blocks. And then we have the large SRAM, which can also be configured to be wider or deeper. The large SRAM, as I mentioned, can be a dual port RAM or a 2-port RAM. And then we have the math blocks. So if I wanted to do, say, some type of a filter operation or something, and I could even write a description of a FIR filter, and I could synthesize it, and the synthesis tool would use the math blocks to do all the multiply accumulate operations that I need. And then once I've verified the functionality of my design, I would go off and create my programming file and program those appropriate flash switches so that the design would run into part.
And then you were also mentioning about error correction on the SRAM. Can you weigh in a little bit on that?
So the SRAM blocks in the microcontroller subsystem, in the ESRAM blocks here, and in SRAM blocks in many of the other blocks, like the CAN controller, for instance, the Ethernet MAC, have an option where we can enable this EDAC, or what we call SECDED, single error detect, single error correct, double error detect. So we can detect 2-bit errors, we can correct single-bit errors, and we can generate an interrupt if we want to on 1, 2, or both. So if we detect an error, if we correct an error, we can interrupt the cortex so it knows that. This is a kind of a reliability thing where if we have any situation where the memories get corrupted, we could go back and fix that. And then we have some IP. We don't have built-in EDAC for the memory blocks in the fabric, but there is some IP you could use, so you could implement a similar function there.
Great. Also, you were mentioning there's different parallel buses, two types of parallel buses interconnecting the devices. And when you're putting in virtual cores, that is a bit of a factor of consideration. Can you weigh in a little bit on those?
Sure. So we have something that's called the fabric interface controller. Every device has one, has FIC0. Some of the devices have a second one called FIC1. And this allows the cortex to interface with the fabric. Now, what you can do with that, you could look at the peripheral set that's in the microcontroller subsystem, and you might say, I wish I had more UARTs, or I wish I had a PWM or something. Well, in our software, we provide a library of some cores that you can use. And you can put those cores in the fabric, and then you can access those cores through this fabric interface controller. So you could actually put some more peripherals here, and you could map those right into the memory space, and it just looks like it's more peripherals available to the cortex. But the other thing that we can do too is there's two sides to the fabric interface controller. There's a side where the microcontroller subsystem and the cortex is the master. We have slaves out here. There's also another side where we could have a master out in the fabric, and we have a slave side, so we can access slaves here, like the spies and the timers and things. So you could actually have another master out here. So we have two different types of interfaces that we can support through the fabric interface controller. We can support either the ARM APB bus, the ARM peripheral bus, which is kind of a simple bus for low-speed peripherals. And then we also support the ARM AHB Light bus, which is the ARM high performance bus. And we have peripherals that are APB peripherals. We have peripherals that are AHB peripherals that are part of the catalog. And we also have bridges, so if you had a mix of AHB and APB peripherals, you would configure the FIC as an AHB, and then we have a bridge that goes AHB to APB, so you could connect your peripherals. Igloo 2 is very similar, but Igloo 2 does not have the Cortex-M3. So some of our customers like the fabric, they like some of the security features and things, but they want a different processor, or maybe they don't need a processor. And so we came out with the Igloo 2 family, which has the same FPGA fabric as you'll see in SmartFusion 2. It has the exact same SerDes. It has the same memory controllers, the DDR memory controllers. What's not there is the Cortex-M3 and some of the peripherals. We still have the block that had the system controller, although we call it the advanced security. But we have the AES 256 and the SHA, and we have this SRAM puff and all those features you saw before. There was a block in the other diagram that said flash freeze, which is a low power mode. It's actually there, it just isn't in this picture. But the same low power modes exist. Over here is where the difference is. Instead of the microcontroller subsystem, we have what we call the high performance memory subsystem. And many of the peripherals that you saw in the SmartFusion 2 are gone. We don't have the SPIs, the I2Cs, and the UARTs and things. We do have the one SPI that you can use for programming that we talked about. We have the ESRAM, we have the flash memory, we have the DMA controllers, the PDMA and the HPDMA, and we have the DDR memory controllers. And we still have the FIX, so we still have the same concept that we described with the FIX, where we could have peripherals out here, or we could have a master out here, and we could access the RAM, the flash memory, and the ES memory. So it's just it's a little bit simpler. We've just eliminated basically the Cortex and the peripheral set that's associated with the Cortex for people that either want to use a different processor or didn't need a processor.
Great.
So SmartFusion is a member of our third generation flash devices. And those devices have a little bit different FPGA fabric, and there are some changes in the Cortex. But where they're similar is we still have blocks that are implemented as standard cell. You see them here in blue again. And we also have an FPGA fabric that has blocks of SRAM, although there's only one size of SRAM. We have our FPGA logic here, and we have the microcontroller subsystem. Now, where there are differences between SmartFusion and SmartFusion 2, we have a block called the supervisor, but the supervisor block doesn't have the AES or the SHA engine or things like that. We don't have the random number generator. We don't have the instruction cache that we have in SmartFusion 2. And we don't have the security feature to block off masters through the AHB bus matrix. And then there are some of the blocks that are available in SmartFusion 2, like the DDR memory controllers, the SerDes blocks. Those aren't in SmartFusion either. One thing that is in SmartFusion, however, is we have some analog components, and we have a successive approximation A to D converter that can do 8, 10, or 12 bits A to D. You have 1, 2, or 3 of those, depending on the device you choose. And then we also have D to 8 converters, and we have 1, 2, or 3 of those. So we have analog components, and we have something called the analog compute engine that's used to drive the components. The analog to digital converters have an analog mux. You can have like 16 input channels. So the analog compute engine would choose one of the channels, would set the sample rate, and then would capture the data when it's finished and make it available where the Cortex could read it, maybe stored in RAM or something like that. So these are different devices. They don't have all the security features that we have in SmartFusion 2 or Igloo 2, but they do have analog where people need analog on board. And we talked about SmartFusion and SmartFusion 2. We have some boards for SmartFusion 2. There's a few different boards. This is the SmartFusion 2 starter kit. The starter kit has a SmartFusion 2 device that sits on what we call a system on module. It actually snaps onto a little baseboard. There's two versions of this, one that has a SmartFusion2 050 and one that has a SmartFusion2 010. This board will allow you to take advantage of the Ethernet MAC that's on board. You can use the USB on the go. It has 64 megabytes of LPDDR memory, so you can connect to that through the DDR controller. It also has 16 megabytes of SPI flash. It's really intended to showcase some of the capabilities of SmartFusion2, pretty much anything except the SerDes, because there's no SerDes capability that's brought out on this particular board. We do have a little breadboard area here where you could connect to the device, and then you could connect that to other logic or other boards if you wanted to.
Now, this same board is also available in a variant for SmartFusion1, correct?
Yeah, there's a system-on module for SmartFusion that you could snap in place of the SmartFusion2.
And these boards are made by third-party?
MCraft.
MCraft.
Yeah, so it's a partner of ours. They actually have a Linux solution that you can run on SmartFusion or SmartFusion2. And so this is a board that they've developed to demonstrate their Linux solution.
So there's two headers down there, the debug and the programming header. Would you briefly mention about the usages of them and what can be interfaced?
Yeah, we have these two connectors right here, and the smaller 10-pin header, that is the JTAG header, and that's where we plug in our FlashPro programmer to program the SmartFusion2 device. And we can program the flash memory that's in the device. We can program the FPGA flash switches to configure the FPGA. We can also debug through that same JTAG connector using a free tool that Microsemi provides called Soft Console. But there's also other tools that are available, Kyle and IAR, for example, that allow you to develop C applications and debug them. And you could use those with SmartFusion2 or even SmartFusion, and you would use this connector here. So you would get the U-Link or J-Link to support Kyle or IAR. You would plug it into this connector, and then you could use those tools to develop your code instead of using Soft Console if you wanted to. Okay. So two variants of this board. We have another board called the SmartFusion2 Evaluation Kit. This board is a little bit more full-featured. It brings out the SerDes capability, and we have a PCI Express Edge connector here, so you could actually plug this into a tower computer if you wanted to and run PCI applications. We have SMA connectors here, so you could bring out the SerDes channels, and you could loop them back, or you could even connect them to a scope if you wanted to adjust your eye patterns and things. This board has LPDDR, 512 megabytes. It has 64 megabytes of SPI flash. Again, you can access the Ethernet using the Ethernet MAC and the connector here. And we've brought out a header here, so you can bring signals out from the FPGA, just kind of general purpose, and you can connect up to other boards or scopes and things through these pins. And then we still have the same connectors. Here's our 10-pin JTAG connector right here that we can use for programming and for debugging code using Soft Console. And then we have the larger connector that we can use with Kyle or IAR. And there's also a smaller connector right here that you can use with some of those tools as well. ARM's defined a little smaller header, so we put that on the board too. So this board is a little bit more expensive than the starter kit, but it gives you access to the SerDes lanes. And then we have the SmartFusion2 Advanced Development Kit. This is the most fully featured board. It has a by 4 PCI Express Edge connector, so you have 4 lanes instead of just one. We have a couple of Ethernet connectors on there. We've got some FMC connectors, so you could actually plug in different boards that have FMC connectors. And we have even more memory and things on this particular board. Again, we still have the 10-pin JTAG connector for programming and using Soft Console, and then we have the programmers or the connectors that you can use with Kyle and IAR if you want to use those tools to debug the code.
One thing is licensing and your tools are concerned. Can you mention what different chipsets work with which versions of licensing for gold and platinum?
So we have a tool set that supports SmartFusion2, Igloo 2, as well as the 3rd generation flash parts, and it's called Libro SoC. And Libro SoC is a collection of tools, some of which are developed by Microsemi, and some that are popular third-party tools. So the third-party tools that are included are Simplify Pro for synthesis from Synopsys, a version of the Model Sim simulator from Mentor Graphics for simulation, and also a debug tool called Identify from Synopsys. All of the other tools, the IDE, the place and route tools, some design entry tools that we'll see, those are all developed by Microsemi. We have two different editions of Libro SoC. There's a free edition that we call Gold. And Gold supports all of the third generation flash devices. So that would be SmartFusion, Igloo, ProASIC 3, and so on. So all of those are in the free edition. And then the SmartFusion2 and Igloo 2 devices up to 60,000 logic elements, up to the 060, that don't have the design security features that we talked about, the parts that have the S suffix. Any device that doesn't have the design security features, that's under 60,000 logic elements, is in the free edition. And then if you want the larger devices that are more than 60,000 logic elements, or any of the parts that have the S suffix, you need to go to the purchased edition.
So we've talked about the different devices that we have, SmartFusion2 and Igloo 2, and we've alluded to this flash technology. So what exactly is that flash technology? Well, what it boils down to is the very basic interconnect that's used to configure the logic and make the interconnections between the logic elements, the inputs, the outputs, and the IOs, and so on. So there are different types of technologies available, and Microsemi uses two different types of technologies. So in the FPGA world, you can find devices that are SRAM based, and they use an SRAM cell to make the interconnects. SRAM devices are reprogrammable, but they're also volatile. So that means every time you turn on the power, you have to reconfigure them. And that reconfiguration can lead to some security risks, and it can also lead to higher power consumption. There's flash-based FPGAs that uses an interconnect that's reprogrammable, but it's non-volatile, so that once you've programmed the device, you don't have to program it every time you turn on the power, but you can change the configuration by reprogramming. And then there's devices that are called anti-fuse devices, or one-time programmable devices. And they're non-volatile, but they can't be reprogrammed. So Microsemi makes two different types of devices. We have flash-based devices, and we also have some older legacy anti-fuse devices. So here we're just kind of comparing the flash switch on the left to a typical SRAM interconnect switch that's used on some other competitors' FPGA devices on the right. And what we have in the flash switches, we have a standard MOS transistor, but we have this floating gate. And it's this floating gate that gets programmed, and it stores charge, and it retains that charge. In fact, we guarantee that we can retain that charge for 20 years if we don't exceed 500 programming cycles. So the advantage is it's smaller, first of all. What does that mean? Why is that an advantage if it's smaller? Well, you can put more interconnects on the die. And if you can put more interconnects on the die, it makes it easier for the software to place and route complex designs. And it ultimately lets customers have a higher logic utilization. You want to use as much of the logic as you can. You can't always guarantee 100% utilization, but we routinely go 85–90% utilization with our devices. The flash switch is smaller in size, so it's lower power, and it's reprogrammable, the same as an SRAM is reprogrammable, but it's non-volatile, so you don't have to configure it every time you turn on the device. And we have an advantage in terms of power because SRAM devices tend to have much more leakage than our flash switch has. We have negligible leakage, so that helps us have much lower power devices, which can be very useful if you're in an application where power is a big concern. Now, the way this actually works is here's a look at our flash transistor, and you can see the source and the gate and the drain. But what we do is we add this extra floating gate right here, and this floating gate is going to be programmed and erased. And we use the hot insertion, we use the electron hot insertion mechanism to program, and we use the Fowler-Nordheim tunneling mechanism to erase the devices. So when the device is in a normal operational state, we'll have 0 volts on the source, gate, and drain. But at programming time, we actually put 16.5 volts on the gate, and we do that by generating these voltages internally. So you're not having to supply 16.5 volts. But when we do that, the channel narrows down here and electrons get excited and they bump together, and some of those electrons get bumped into the floating gate, and eventually that floating gate will be full of electrons, and then we can take the voltage back to 0 and those electrons stay there. So that floating gate is now charged, and that can turn on that pass transistor so we can make these connections, and that charge stays there until we go back and we erase the device. So once we've programmed those floating gates that we wanted to program, they have that charge on them, and charge will start to leak off over time, but we guarantee that we can hold this configuration for 20 years if we don't exceed 500 programming cycles. And if you wanted to extend past 20 years, you could just program again. You kind of refresh everything. Now when we go to erase the device, we put voltages on the gate, the drain, and the source, and we put a negative 12 volts on the gate. And what that does is that pushes all the charge out of the floating gate, and we do that until all the charge is gone. And then if we go back to our normal operational voltages, if the gate has no charge in it, then it doesn't get any more charge until we go back and we program. So those are the mechanisms that are going on when we're going through the programming cycle. And first we'll go through and we'll erase all of the flash switches. Then we'll program the flash switches that need to be programmed based on the programming file we created for our design. And then we go back and we verify that all the correct switches were programmed and that we didn't program any switches that we didn't intend to program. So that's what's going on in the programming function. And those internal voltages, we saw the 16.5, the -7, and so on, the -12.5, those are all generated internally. We have internal charge pumps that generate all those internal voltages.